Hello. Welcome back. See, today we have an actual cat cam again. In fact, let's just make it big. Let's just get wow. Look at this guy. Look at him. He's so sleepy. Sunbathing, getting the warmth, soaking up those rays. It's been cold and dark for so long. He has to come celebrate. Excellent. All right. So we will be joined by Jules today, so all of you can have a big sigh of relief, and we're gonna just get right into it. So today we're talking about useful trees. Uh, Last time we talked about trees in general, we talked about them sort of in a theoretical, abstract way of saying, "Hey, you can organize data in trees, and that's useful, I guess." Not super useful. Today we're going to talk about trees that actually let us compute things efficiently, um, which is exciting. So let's get into it. So let's talk about keeping a list sorted. Um, you probably talked about keeping a list sorted in your 201 equivalent class where we talk about inserting into a list that's sorted and so on and so forth. So let's just kind of go back and review what's going on there. So what is the problem? The problem is we have a list of items and we want to maintain them in sorted order at all times. Meaning if we're adding things, we want to put them into the list so that the list remains sorted, and we also want to be able to see what items are in the list and so on and so forth. So what is the fastest algorithm you can come up for insert and get, for adding things and checking if things are there, or removing? We won't talk too much about removal today. We'll just focus on insert and get. And how fast does it run? And how fast should we be able to get it to run? Hmm. Hmm. So here we go. We're gonna do a little. I'm gonna do a little weird today. So here we go. We have a list of sorted items in an array. This lovely illustration, this boxy array situation. And so the question is, what algorithm do we use to do finds and inserts, gets and inserts, right? What item do we use? Or algorithm do we use? So the the first algorithm you learn is like a for loop. So let's put a for loop in here. And I'm going to use pseudocode, aka Python. Nope. And we'll use a fixed width. Oh, why did that make it short? Weird. Oh, oh, oh. Okay, sure. We say for item in list. Or actually we'll say def find find target for item in list if item equals target, targ, which is a kind of shield, uh, return true. And then down at the bottom, we just return false. Okay? So that's our find method. And so that's a really easy one to write. This is very short. Um, the problem is, oh, we need a list parameter, right? So the problem is here, if I try to go find 5, I'm going to start at the beginning and I'm going to look at 1. And then I'm going to look at 3. And then I'm going to look at 5 and I find 5. Right? What if I want to find 11? Well, then I start at 1 and I look at 3 and I look at 5 and I look at 6 and I look at 7 and I look at 9 and I look at 11. Ah, I found 11. So how fast is this? Chat. I'm looking over at chat as if it's going to light up with, "Oh, this." It's just this is a recording. Future Ben has much more fun than past Ben. Anyway, uh, so it's linear, right? It's linear. If I'm looking for something, suppose I try to find like find uh ah find, let's put in like cat emoji, right? Is cat emoji's not even in there, right? So it's like 1, 3, 5, 6, 7, 9, 11, 15. No cat emoji. So I had to look through the whole list to determine whether cat emoji was in there. So that's kind of, it stinks. So this horrible situation is a big O of n, right? Every time I add an item to the list, this thing in its worst case will take longer to execute. And so if I double the size of the list, this will take twice as long to execute. All right, so let's look at another solution. You probably remember, if you actually were in my 201 many moons ago and we were in person, you probably saw me rending phone books with my incredible strength. Take that, one thin layer of paper that's binding together this phone. So how did that work? So we say def, this would be binary search. Binary search. And so for that, we have a target and a list. And and so we look at target index or middle index, mid index equals length of list divided by 2 if list at mid index is equal to target. So we look in the middle of the list. So we'll look, let's see, there's 8 values here. So 8 divided by 2 would be index 4, which would be 7. So we would look at 7 and we would say, is 7 5? And we go, no. But if we were looking for 7, we would say, yes, I found it. So let's put that in there. We would return true. Else, or elif, list mid index. Well, what if, so in the case we're looking for 5, we're going to find 7, which means that the thing we find in the middle is greater than target. What are we going to return? Guys, what do we return? What do we return? Huh? Huh? What? I don't know. I'm just giving time. No one's going to say anything to me. We're going to return binary search. Same target. And then I'm just going to bump this into the next line. List up to mid index. Whoops, not the second bracket. Mid index. My typing is so much slower today. Oh, no. Like that, right? And then lastly, else. So if we don't, if this is actually less than that, right, which would have to be the remaining case. Like that, right? So if you're not familiar with Python syntax, this means do the binary search on the first half of the list if the target is less than the middle item, and this is Python for do the binary search on the second half of the list. So this is binary search. So how fast does this run? Well, we have to ask how many times does this recursion get called? Because the recursion is a form of iteration. So we have to ask ourselves, well, how many times is this recursion called? So let's think about that. So if we're finding 5, right, we look and we see, oh, okay, it's less than 5 is less than 7. So we're going to do our binary search on the oh, no. We're going to do it on the first 4 items of this list, 1, 3, 5, and 6, which is 4, which means I'll look at 5 and boop, oh, I found it, I'm done. Okay, so that was 2 iterations. What about 11? Well, 11 would be greater than 7, and so we look at this, and we get 3 divided by 2, which equals 1, which would find us 11, which would be another 2. Well, what's our worst case? Our worst case would be the thing's not in here. So let's look for, 17. So we would look at 7, we would go over here to the last 3 items. Boop, boop, whip, boop, boop. I said boop, 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 boop. We look at these last 3 items. The middle item will be 11, so we'll look at that. And then it would be the right-hand side, so we'd look at 15. So this would be now our third comparison. We would see that it's greater than 15, but we're only looking at one item, and it's not there. So we actually do need a base case. If len list equals 0, return false, right? So eventually we would say, okay, well, give me all the elements greater than 15. There aren't any, and we're done, right? So how many times is this working? Well, this algorithms is making the size of the lists smaller by half each time we iterate, right? Every time I iterate, I'm doing this halving operation. So then the answer to this question, how many times it iterates, is also the answer to the question of, if the length of the list is n, how many times can I divide n by 2 until I get 1? That sounds familiar, right? Like that sounds like log. And that's the answer. It's log. So this is logarithmic performance. Nice. 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 So we did it, right? We have logarithmic performance. That's better than linear performance. Can we do better than logarithmic performance? Probably not. So we're done, right? Right? Guys? Guys? Jules? Jules? Hey. Hey, Jules. Are we done? Jules, are we done? Jules, are we? Okay, you're right. We're not done, right? Because we haven't done all of the operations. See, Jules has taught 341 now. This is his third time. He's kind of over it. All right. So then what do we do? What do we do here? So now we have to do insert. Well, how does our insert work? Well, what we can do is we can use binary search to find where we would insert the thing, right? We presume that when we're inserting, the thing isn't already there, but binary search will still find us the spot in the list where we need to insert 2. So we take 2 here, and we look at the middle item 7, and we say, you're less than 7. So 2 is going to be inserted into this sublist. Excellent. So then we call insert on this smaller sublist. So we're still doing binary search, but we're doing like binary insert. So we're doing an insert on the left-hand side, the left-hand side, as opposed to the right-hand side. So you could almost say 7 was the first thing we looked at, and we saw that it was greater than 2, and then we looked to its left. That'll be relevant later. Ding. All right. So I get excited about trees. So we're going to put it over here, and we're going to consider, where does it go? Look at this little red line freaking out. Where does it go? All right, so then we're going to look at 5, and we're going to ask, where do you go? Well, you go left of 5, left of 5. And then we're going to go over here, and we have 1 and 3. So we're going to look at 3, and we're going to say you go left of 3, which means, boop, it goes in here. But oh no, guys, there's no array slot for here. We can't put it in 0.5, right? If this is index 0 and this is index 1, 2, 3, 4, 5, 6, 7, right? I can't just be like, I will snuggle you into index 0.5. No. What do we have to do? 15, go to the right. 11, go to the right. 9, go to the right. 7, go to the right. 6, go to the right. 5, go to the right. 3, go to the right. So, here's the thing. We're using an array for this. We can, or a linked list. Well, actually, a linked list. Well, okay, there's other problems if you use a linked list, but we're not going to talk about that right now. The reason a linked list would be slow is you can't just jump straight to 7. You'd have to start at 1 and then go 1, 3, 5, 7, and then you would have to start over and then go 1, 3, right? So a linked list doesn't even let you use binary search, right? So we have to use an array for binary search to get that logarithmic speed. So, but if we use an array for binary search, we have to shift everything to the right to make room for the thing that we're inserting. And what does that look like? What's the speed of that, right? I had to drag nearly every element over. So if you're saying linear and thinking linear, you're right, it's linear. So we have really fast, really fast finds. We get logarithmic performance for find, but we have excruciatingly slow like inserts because we have to do all the shifting. Blah. How fast was that? Find, linear. Insert, oh, so sorry. Find was logarithmic. Insert was linear. We can do better in principle. It's it's going to take a couple weeks to explain fully how we can do better. But but we can do better. So, how are we going to do better? So we talked about binary trees. We talked about binary trees previously. So let's see, can we use binary trees to make this faster? So now we're going to create a data structure that lets us store data in sorted order, just like we were trying to do. And then we want to be able to do this binary search effectively. For an insert, what does it look like? What is its performance? How does it work? All right, so let's go back here. So if I'm gonna do a binary search on this tree, right? Or sorry, on this list, and let's suppose we're looking for negative. Let's suppose we're looking for negative infinity or something, like some value that doesn't exist in here. Where do we start? Where's the first place we look? It's 7, right? So let's make a tree and let's make the root 7. Okay? Cool. So now, if I'm going to insert values less than 7, where do I look next? 5. So we'll make 5 the left child of 7, right? Because 5 it is where we would look next in a binary search, right? And so 5 is representing all of the values less than 7. Okay? So then what if we want to insert or look for 6? Where does 6 go? Well, 6 will go 6. 6 will go to the right of 5. Ooh. What about if we're looking for values less than 5? Well, we'll look at 3. And what if we're looking values less than 3? We get 1. Interesting. Hmm. All right, what about greater than 7? Well, we'll look at 11 because that's the middle value over here. And we'll draw an arrow. And then 9 will be less than 11. And then 15 will be greater than 11. That's a binary tree, and it still represents all of the values. So now if I want to do a find, what do I do? Well, I look at the root node. So let's make a box over here. And this will be the binary search tree. And it's going to have a root, a node point root, right? And that is going to point to the root. Okay? So now, how do we do a find with this new tree operation? So what we do, how do we do a find? We're going to come over here. So we're gonna do it again. Binary. Oh, we didn't make it. We didn't make it fixed with, guys. All right. Def find on a node. So we're gonna call find on the root to start. If node data equal. Oh yeah, find on the node. The target, because we still need that target. All right, grit. Grit! Grit! Grit. Let's put it down here. We can't interrupt grit. The truest of. Grit. See, I've been at UMBC for like over a dozen years. So True Grit and I, we're on just grit terms. I can call we're that close, right? So that's what you get. That's your like over a dozen year thing. So then we return true, right? If the thing we're looking at, this is like becoming some sort of weird Python C++ amalgam. If just to continue to make things confusing. Node data is greater than, or sorry, is is greater than the target, right? So if the thing I'm looking for is less than the node that I'm looking at, what do? Well, I just return find on node left target. We don't need this anymore. Get out foul spot. Right? This is like live coding in a PowerPoint presentation, but when you need the visuals, I would do this on a whiteboard if I could. But we don't have those things. All right, so cool. So we look on the left-hand side. So this is just our recursive call from the earlier binary search, remember? It's just this thing. But instead of doing array operations, I'm doing tree ones. It's fine. It's fine. All right, cool. And then so then we get else. Return find node right target. Cool. So we need a base case here. Well, what is a base case? So what the base case means, like if we're not finding it. So right, if I ask for 0 in this case, I'll look at 7 and then I'll do find left and I'll look at 5 and I'll do find left and I'll look at 3 and I'll do find left and I'll look at 0 and I'll do find left. And then what, right? Well, down here, this node is going to have null pointers, right? These will just be null. So what we need to do is we need to add a base case. If node equals null, how about that, huh? Nice. Right? So that's our find. That's it. How fast is it? Well, the answer is log. We'll talk about efficiency in a second, but we're just talking about how this tree works. All right, well, what about insert? Right? We had that weird shifting problem for insert. That's pretty much it. Uh, you can't actually do it this way. What you would have to do is, because you would still need to connect the parent to the child, you would say if node left, you would do this, right? So if I have a left child, resume the search. If I don't and it's null, then node left equals new node target. and then you'd repeat on the right-hand side. That's it. You don't have to do any weird, awkward shifting. That's it. That's all you have to add. Hopefully, this recursion isn't freaking you out. Because if it's freaking you out, you absolutely must go review recursion. And there's problems in your homework that will help you do a review of recursion if recursion's giving you weirdness. But in general, what we're saying here is, if I'm going to do a search on this node, if this node isn't what I want, then I'm going to resume the search on its left subtree, represented by the left subtree's root, which is just my left child. Right? So conceptually, you're just kind of passing the buck. You're just kind of saying, "Oh, I don't really know the answer to this. I'm just going to ask my left subtree, because if it existed, it would be over there." And so the big property of a binary search tree is each node, right? Each node has a value. All of the nodes to its left, all of them, everything in its left subtree has to be less than it. And everything in its right subtree must be greater than it, right? Where would 4 go in this tree? Where would 4 go? And the answer to this question is it would be the blank child of blank. So the right child of 9 or the left child of 6. So in this case, the answer is it would be the right child of 3. That's where 4 would go, right? Because it has to go left of 7, it has to go left of 5, and it has to go right of 3. Okay? And then we'll grab an arrow. Arrowed. Boom. Okay? So that is the property of a binary search tree. This is probably the point in this. My screen is flashing. I apologize. This is the hopefully the point in the semester where you'll start to get more comfortable with recursion, because you can kind of see it. Like the tree is kind of like a visualization of the recursion, and it actually gets to the point where writing these recursive solutions is much easier than doing this iteratively. Trust me. You will have a homework assignment if it's not already out. I don't think it's out. You will have a homework assignment that says, like, that makes you do tree operations iteratively, and boy, is it a rotten pain in the butt. All right. Let's talk about the would you rather, and then we're going to talk about traversals, and then we're going to be done. We're going to be done for the day. All right? So we sort of did some live coding here. This will be deleted from the slides. Why? Don't delete this from the slides. Well, it's also going to be the collaborative thing of your homework. So even if you have to watch this again and type this out into legal C++ code, also I just want to reset it for next semester. It's like resetting an escape room. Okay. Excellent. So, let's do the would you rather. You can taste with your fingertips. Your fingertippies. You can taste with them. If you wear gloves, you will taste the inside of the gloves. I love this would you rather because it's cephalopod. Cuttlefish have these powers mostly, and octopodes. The other one is your skin changes color according to your mood. So if you're happy, so your skin has a color for all of your moods. So if you're happy, you might be orange, and if you're sad, you might be blue. But it might, whatever color, it's just you will always consistently, if you're excited or sad or nervous or anxious, you'll have a color for all of those things. So people could, you'd be wearing your heart on your sleeve, or basically you would have to be fully clothed and masked for people. You'd be a terrible poker player. I also love these because they're both kind of cool, but also kind of annoying. So we're gonna pause so you guys can so you guys can ponder this. So Huh? Ha! Right. I'm like camouflage, like cuttlefish, swimming through the water, having fun. All right. I hope that worked. We gotta have fun with this somehow, right? We gotta have some amount of fun. All right. Let's wrap. Let's get into the end of this. Um. So what is a traversal? A traversal is an algorithm that looks at each element that is stored in your data structure. All right? So, what does a linked list traversal look like? What does that look like? We're just going to do, again, this is where I would use a whiteboard. Um, so we would say cur equals head, while cur doesn't equal null, or just say while cur, you can do something with cur, print it out, look at it, inspect it, update the data, whatever, and then cur equals cur next. That's a traversal for a linked list, right? Cur will take every value of the linked list data structure and allow you to do something with it. So what does a tree traversal look like? So before we did cur equals head, here we're going to do cur equals root. And so there are three different kinds of tree traversals. Pre-order, meaning me first. I get to go first. I'm special. Post order is the polite one. Everyone first. I'll go last. I'll take up the rear. It's fine. And then in order, like we should all align ourselves by our heights, right? So there's three different options there. So let's look at a pre-order traversal. So a pre-order traversal, let's suppose we're printing out the value as a visit, right? So we're talking about visits. So we in this slide down here, visit could mean print out, inspect the value of, update something, whatever, right? It's a visit. Like you're visiting each node. So we're just going to say visit root. Because remember pre-order, this is pre-order we're doing right now. Also, let's get the oh, this is just okay. But I cannot work with these conditions. Goodbye. And then new, sweet. Excellent. Excellent. Okay. Why aren't these just prepared ahead of time? Because if they're all there, it's easy to get overwhelmed. All right. So we're gonna visit root. So this is a pre-order for binary search tree, which will be BST for short for the rest of the semester because you get tired of typing it out. Right? And then this will be, we'll call it def pre. Actually, yeah, we'll just do def pre-order node. All right, so in the BST, you would start by calling pre-order root. Okay. Then you're going to do a pre-order of your left-hand not visit root, visit node. Then you're going to do node left. Then you're going to do pre-order node right. That's it. And that visits all the nodes because it's the suborder thing. So let's look at the tree. What order would they get printed out in this tree? Just put these over here. So pre-order is visit left right. So up here, I would visit 7, which means I would print it out. Then I would go left, and then I'd look at 5, and I would say, what do I do with this? VLR, visit left right. So I would visit 5 by printing it out, and then I would go left, and then I would visit 3, and then I would go left, and I'd visit 1, and then I'd go back up to 3 in the unwinding recursion. But I've already visited it, so I'd go to right, and then I'd say 4. Actually, this is just not a good way of illustrating this. Pause. All right, let's see. Can I do a fun cut? Bring! Here we are. We're back. All right. So 7, 5, 3. It doesn't really matter. 6, 1, 15, 12, 18. Whatever. Doesn't matter. Bloop, 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 bloop. So for a pre-order is visit left right. So each next to these, I'm going to do visit left right on this one. So I'm going to visit first, which means print out 7. Then I'm going to go left. So that means we're going to visit, we'll go to this one, and then we're going to visit this one by printing it out. Then we're going to go left again, which gives us VLR over here, which we visit 3, cross it out, then we go left. Actually, yeah, we can go left. We've gone left on all of these. Then we do VLR. We're going to visit 1. Then we're going to go left. There's nothing there. Right. There's nothing there. Then we come back up here. We go right of 3. There's nothing there. We go up here. We go right of 5. There's nothing there. So 6. And then we come up here and we go right of this. So we get VLR. And so we get, we're going to visit 15. So we're going to print it out. Then we're going to go left to 12. So VLR, visit 12, left, there's nothing there, right, there's nothing there. We've already done left. Then we're going to go right, and then we're going to do VLR here, and we get 18. Ta-da! And then, let's see, through the magic of editing. Oh, look at that. All right. I sure hope this comes out. All right. So now we've got this. Let's do in order. So this is still a binary search tree. We're going to do in order. In order is left visit right. Okay? So here's our printout down here. And we're going to do left visit right. Okay? So we're not going to print out 20 because we're going left first. Left visit right. Not going to print out 15. We go here. Left visit right. And now we're left. There's no left. Visit. We'll print out 10. Right. There's no right. We go back up. Here we finally get to visit 15. Cross that off. Then we go right, which there is no right, so we're done. Then we come up here. We can visit 20. Then we can go right, which will come down here to 25. Left visit right. So I'm going to go left first. Left visit right. And then I'm going to have 21. So 21, I'm going to go left. There's nothing there. Visit 21. Right. There's nothing there. Go back up here. Visit 25. And then I'm going to go right to 26. And right. And then we're done, and we're done. So that's it. All right. We're going to do, again, some more magic. Walla, 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 walla. Bam! There we are. All right, back to Chrome. So, how do we modify our code? Oh, I'm not going to do post order. Do that as an exercise. Get a piece of paper, draw a tree, and check your work. There'll be some examples on the next homework. So, In the BST, you would call by, okay, so what if we wanted to do in order? What do we change? We went visit left, right. Now it's left, visit right. That's it. That's all the change we make. Isn't recursion grand? This is 3 lines of code to visit the whole thing. It's really nice. Oh, actually, we would want to change these. What's interesting about in order for a binary search tree? What's interesting? If this is a binary search tree, in order will visit everything in sorted order. Which means if you have a binary search tree, we've described an insert, and a get, an insert and a find, and then we've also described how you recover the actual list if you want to. What is the efficiency of this? It's linear. You visit all the nodes once. So here's where we have the bad news. Here's the bad news. So how long does insert take? Well, insert in its worst case has to go all the way down to the bottom. And if it goes all the way down to the bottom, that means the performance is based on the height of the tree. Well, how short can the trees get? Last time we saw that the shortest tree with the most possible things in it is a perfect tree, and the height of that tree is logarithmic. That's good. That would mean that our inserts are logarithmic. But what's the tallest a tree can get in the worst case? Let's just focus on this subtree. What's the worst case scenario? Well, the worst case scenario is basically that, well, this what is going on. But basically, pretend the arrows are all going the right direction. The worst case scenario is the tree is linear in its depth, meaning insert would then be linear. So this video is now 43 minutes long, and we've accomplished nothing? Is it nothing we've accomplished? I think it's nothing. I think we accomplished nothing. But there's light, there's hope at the end of the tunnel. What is that hope? What if we figured out how to keep the tree short and not tall? Tall trees, bad, because you might get linear performance for inserts. So, next time we're going to do a little bit of review, and we're going to introduce AVL trees. AVL trees are trees that self-balance themselves so that they remain short. Then we're going to talk about red-black trees. And there's 2 lectures for each of them. So we're going to spend a month talking about the problem of keeping binary search trees short. It's hard to do, and that's why we spend a lot of time on it. So look forward to that. It's actually a lot of fun. I think it's a lot of fun. And I think you'll have a good time balancing these binary search trees. And the whole goal of balancing binary search trees is to get our insertion performance to be logarithmic. That's it, right? If we don't balance them, insert linear. And that's bad. That's no better than using an array. So the whole next month of class is just going to be balancing binary search trees. All right, everybody. That's all I got for today. This lecture just runs long because there's a lot of ground to cover. And next time, onward and upward. So have a nice day. Goodbye. Goodbye, future Ben. Bye.